Welcome to today's explainer. If you've ever been tinkering with a microcontroller and suddenly found yourself staring at a component that just needs way more power than your tiny little chip can provide, well, you are definitely not alone. Today, we're demystifying the 2N3904 transistor. We're going to see exactly how this little three-legged component acts as the ultimate super versatile solution for driving high current loads, amplifying signals, and honestly, so much more. Let's just dive right in.
Think about this for a second. How exactly does a tiny, microscopic whisper of an electrical current effectively control a massive, roaring flow of electricity in a totally different part of the circuit? I mean, that right there is the core superpower of the transistor. It essentially acts as an invisible electronic valve. It takes a low-power digital command and safely directs a much, much larger analog flow. Okay, let's dive into this anatomy to action masterclass. Here's how we're breaking it down today. First, we'll meet the 2N3904. Then, we'll look at how it actually works, dive into its switch and amplifier modes, cover the essential rules and limitations, and finally, wrap up with how to find a reliable replacement when you need one. All right, part one, let's meet the 2N3904, the anatomy of a tiny giant. So, looking at this ubiquitous, small-signal silicon device, which you'll almost always see housed in this compact plastic shell known as a TO92 package, we really need to decode some datasheet jargon first. It's an NPN-BJT, which, sounds like a mouthful, but that just stands for bipolar junction transistor, and the NPN part tells us it's basically a microscopic sandwich of negative, positive, and negative semiconductor regions. And that specific arrangement, that dictates exactly how electricity flows through the device and how we actually need to connect our power supplies to make the whole thing work. Now let's talk about the physical pins. If you hold the 2N3904 with the flat face pointing right at you and the leads pointing downward, you read them from left to right. Pin 1 is your emitter. Pin 2, right there in the middle, is the base. And pin 3 on the far right is the collector. Now, I have to give you a massive word of warning right off the bat here. TO92 packages are not, I repeat, not universally pin-compatible across different manufacturers or transistor types. You cannot just blindly swap components just because they look identical. Seriously, always check your datasheet. Moving on to part 2, how it actually works, the internal mechanics.
So we know the pins, right? But how does that middle pin, the base, actually control the main flow of electricity? Well, it brilliantly comes down to one really simple mathematical relationship. IC is approximately equal to beta times IB. And hey, don't let the Greek letters scare you off. IC is simply your collector current. That's the big, heavy load you actually want to drive. IB is your base current, that tiny little control signal coming from your microcontroller. And beta, which you'll also see written as HFE on datasheets, is just the transistor's current gain. Essentially, that tiny base current acts like a multiplier to create a much, much larger collector current. Just check out this number, 300. According to the onsemi datasheet, under very specific test conditions, the 2N3904 can have a maximum DC current gain of up to 300. To put that into perspective, that means one single solitary milliamp of current pushed into the base could theoretically allow up to 300 milliamps to flow through the collector. It's crazy. It perfectly isolates the incredible multiplier effect of this tiny little piece of silicon. Now, keep in mind, this HFE value isn't perfectly fixed, right? It fluctuates based on temperature and current, but it really shows you the sheer amount of leverage this component gives you. All right, part 3, switch and amplifier modes, basically putting this thing to work. Now, what's really interesting here is contrasting how the component actually behaves. We have two main ways to use it, starting with its most popular job, acting as a switch. On one side, we have cutoff. If the base current is 0, the transistor is completely off. It acts exactly like an open mechanical switch, literally 0 current flows. But on the other side, we have saturation. If the base is driven high with enough current, the transistor turns strongly on. The path from the collector to the emitter conducts beautifully, acting just like a closed, fully connected switch. Let's actually ground this theory into something you can easily throw together on your workbench right now, a basic 5-volt LED driver circuit. So your LED and its current-limiting resistor are connected between 5 volts and the transistor's collector, and the emitter just goes to ground. Step 1. Your microcontroller control signal is low. The 2N3904 is off, and the LED is pitch dark. Step 2. Your microcontroller sends a high signal, pushing a tiny current through a base resistor right into the base pin. And step 3, this instantly turns the transistor on. That allows the much larger current to flow from the 5-volt source through the LED into the collector
out the emitter and straight to ground. Boom, the LED lights up.
But hey, it's not just a simple on and off switch. If we operate the 2N3904 in what's known as the active region, which is basically anywhere between cutoff and saturation, it actually acts as an amplifier. Think about it. A tiny fluctuating variation in base current, like say the super weak electrical signal generated by a microphone capturing your voice, produces a much larger, perfectly mirrored variation in the collector current. That specific trick makes the 2N3904 absolutely incredible for audio preamplifiers, sensor amplifiers, signal conditioning, and even building small RF circuits.
Which brings us to part 4, rules and limitations, staying within the lines.
Because as incredibly versatile as this component is, it is definitely not invincible. If you don't respect its boundaries, you're absolutely going to let the magic smoke out of the silicon. You cannot ever just hook up 5 volts directly to the base pin. The base emitter junction acts very much like a simple diode, so if you don't limit the current flowing into it, it will literally pull as much current as the power supply can provide, and it will instantly destroy itself. You absolutely must always use a base resistor. That calculates and limits that tiny control current, protecting the junction while still ensuring reliable saturation.
And beyond just the base resistor, the datasheet gives us some absolute hard limits. First, do not exceed 40 volts across the collector and emitter. Second, do not exceed 6 volts of reverse voltage on the emitter-base junction. And critically, 200 milliamps is the maximum collector current. The specs are crystal clear here. That is a hard ceiling, guys, not a suggested cruising speed. If you try to continuously run 200 milliamps through it, you're going to push right up against its 625 milliwatt power dissipation limit. And no, before you ask, strapping a tiny little heatsink to a plastic TO92 package will absolutely not save it if you push it beyond those thermal limits.
Let's move to part 5 and see how this all builds up, finding a replacement, or what I call the benchmarks.
So what exactly happens when your circuit suddenly demands 500 milliamps, or, you just accidentally blew up your very last 2N3904 and desperately need a substitute? Comparing the data is a total lifesaver here. Look at the 2N222. That is your best general replacement for switching because it handles up to 600 milliamps, literally 3 times the current of our 3904. Now, if you're doing small signal audio work, the BC547 is a fantastic alternative. Need even more current for something like a motor? The BC337 can handle roughly 800 milliamps. But please look at the pin compatibility. I am reminding you one more time, the BC547 and BC337 usually have completely different pinouts than the 2N3904. Always verify before you swap. So with all of these beefier alternatives out there, why does the 2N3904 remain one of the most beloved and widely used general-purpose transistors in the whole world? Well, it really comes down to this perfect storm of traits. It is incredibly inexpensive, it's highly versatile for both switching and amplification, it's impressively compact, and you can find it practically everywhere, literally at any electronic supplier on the planet. It is simply the reliable workhorse of low-current digital and control circuits. Which leaves us with this final thought. You now know exactly how to leverage this tiny giant to control up to 200 milliamps using a microscopic base current. But if that 200 milliamp limit is a strict absolute maximum, what component are you going to reach for when your next massive electronics project demands serious, heavy-duty power? Keep exploring, keep checking those data sheets, and we'll catch you on the next explainer.